Retrieval-Augmented Generation, or RAG, is a revolutionary architectural pattern in AI that blends information retrieval systems with generative large language models. This combination addresses the limitations of static LLMs, such as knowledge cutoffs and hallucinations, by enabling access to dynamic or private enterprise data without expensive retraining. In this video, we'll explore the fundamentals of RAG, its components, and why it's transforming enterprise AI. Let's start by understanding the core problem RAG solves and how it empowers organizations to leverage up-to-date information for smarter, more reliable responses. Static LLMs are powerful, but they're limited by their training data. They can't access new or proprietary information unless retrained, which is costly and slow. RAG solves this by integrating a retrieval system that fetches relevant data in real time, allowing the model to generate responses grounded in current enterprise-specific knowledge. This approach mitigates hallucinations and ensures the model's answers are accurate and contextually relevant. By overcoming knowledge cutoffs, RAG makes AI more adaptable and useful for business applications. Standard RAG pipeline consists of three main stages: ingestion and processing, retrieval, and generation. First, documents are ingested, processed, and converted into vector embeddings, which are stored in a vector database. When a user submits a query, it's embedded using the same model, and the database performs a similarity search to fetch the most relevant text chunks. Finally, these chunks are appended to the user's query and fed to an LLM, which generates a precise response. This pipeline ensures that answers are always based on the most relevant and up-to-date information. First stage of a RAG pipeline is ingestion and processing. Here, text is extracted from documents and divided into manageable chunks. These chunks are then converted into vector embeddings using an embedding model and stored in a vector database. This process ensures that the data is ready for efficient retrieval and generation. By breaking down documents and embedding them, RAG systems can quickly access relevant information when needed, laying the foundation for accurate AI responses. Once the data is processed and stored, the retrieval stage begins. When a user submits a query, it's embedded using the same model as the stored chunks. The vector database then performs a similarity search to find the most relevant chunks of text. This ensures that the AI model receives contextually appropriate information, making its responses more accurate and tailored to the user's needs. Retrieval is the heart of RAG, connecting queries with the right data. Final stage in the RAG pipeline is generation. Here, the retrieved chunks are appended alongside the original user query into a template prompt. This prompt is then fed to a large language model, which generates a response based on both the query and the provided context. This method ensures that the AI's answers are grounded in real relevant data, reducing hallucinations and improving reliability. Generation completes the RAG cycle, delivering precise and trustworthy information. Chunking is a critical process in RAG, involving the breakdown of long documents into smaller, discrete segments of text. This is necessary because LLMs and embedding models have strict context window and token limitations. By creating focused chunks, RAG systems prevent embedding vectors from losing specific semantic meanings, ensuring that each piece of information retains its value. Chunking makes it possible to efficiently process and retrieve relevant data for AI generation. Chunking is essential because both LLMs and embedding models have strict limits on the amount of text they can process at once. If documents are too long, important semantic details can be lost, and embeddings may become noisy. By keeping chunks focused and manageable, RAG ensures that each segment retains its specific meaning, making retrieval and generation more accurate. This process is foundational for building effective RAG systems. Size chunking splits text strictly based on a set number of characters or tokens, such as every 500 characters. While this method is simple and easy to implement, it can violently slice sentences or paragraphs in half, destroying semantic context. This loss of context can make retrieval less effective and generation less accurate. Understanding the limitations of fixed-size chunking is important for designing better chunking strategies in RAG. Cursive character text chunking uses a hierarchical list of separators, such as paragraphs, sentences, spaces, and characters, to split text. This method attempts to keep structurally related units intact until the chunk size constraint is satisfied. By preserving paragraphs and sentences, recursive chunking maintains semantic context, making retrieval and generation more effective. This strategy is more sophisticated than fixed-size chunking and is preferred for high-quality RAG systems. Chunk overlap is the practice of repeating a certain number of characters or tokens from the end of one chunk at the beginning of the next. This ensures that semantic context crossing the boundary of a split is not lost. By preserving vital pieces of adjacent information, chunk overlap prevents important details from being decoupled, making retrieval and generation more robust. It's a simple yet powerful technique for maintaining context in RAG system. Selecting the optimal chunk size for a RAG system depends on several factors. The nature of the content matters. Short medical definitions require smaller chunks, while complex legal contracts need larger ones to preserve arguments. Embedding model constraints in the target LLM's context window also play a role. It's best to tune chunk size experimentally, using grid search and validation metrics to find the balance between accuracy and performance. Semantic chunking uses natural language processing or embeddings to find natural breakpoints in text based on meaning, rather than static token or character counts. For example, it might compute the cosine similarity between sentences and split the document only when the similarity drops below a threshold, indicating a shift in topic. This approach ensures that chunks are meaningful and contextually relevant, improving retrieval and generation quality. Its embeddings are generated by deep learning models like BERT or ADA002. They capture semantic meaning, synonyms, and conceptual relationships in high-dimensional continuous vector space. For example, they understand that feline is close to cat. Dense embeddings are powerful for semantic search, enabling RAG systems to retrieve contextually relevant information based on meaning rather than exact keywords. Sparse embeddings are represented by traditional keyword or term frequencies, such as BM25 or TF-IDF. They focus on exact keyword matching and structural syntax, making them highly effective for tracking specific IDs, codes, or specialized terminology. While less powerful for semantic search, sparse embeddings are useful for precise retrieval tasks where exact matches are critical. Dense embeddings capture semantic meaning and relationships, making them ideal for understanding context and synonyms. Sparse embeddings, on the other hand, focus on exact keyword matches and are better for tracking specific terms or codes. Choosing between dense and sparse embeddings depends on the retrieval needs of your RAG system. Both have their strengths and can be used together for optimal performance. Modern LLMs have massive context windows, but passing an entire 100-page PDF directly to them isn't practical. It leads to high latency, increased costs, and the lost-in-the-middle effect, where LLMs struggle to recall specific information buried deep in large prompts. RAG systems solve these issues by retrieving only the most relevant chunks, ensuring efficient, accurate, and cost-effective responses. Document Transformer sits between document loading and vector storage in a RAG pipeline. It modifies document elements by parsing metadata, translating text, filtering out boilerplate, or rewriting headings. This ensures that the embedding process captures high-signal data, making retrieval and generation more accurate. Document transformers are essential for preparing documents for effective chunking and embedding. Markdown-based and HTML-based chunkers are structure-aware tools that parse specific tags such as headers and paragraphs. Instead of splitting text mid-sentence, they group content logically based on sections, ensuring headers remain with their corresponding paragraph blocks. This approach preserves document structure and context, making retrieval and generation more effective. Retrieval bottleneck in RAG refers to the phenomenon where the quality of generation is limited by the accuracy of the retriever. If the retriever fails to surface relevant context or fetches noisy, irrelevant chunks, even the most capable LLM will produce flawed or incomplete answers. Ensuring high-quality retrieval is critical for effective RAG systems. Rounding is the process of forcing an LLM to base its responses strictly on verified provided context, the retrieved documents, rather than drawing from its internal pre-trained weights. This acts as an anchor, minimizing hallucinations and ensuring that answers are accurate and trustworthy. Rounding is a key principle in RAG, making AI responses more reliable. BindEncoder embeds the query and documents completely independently into vectors. Retrieval is performed using fast vector similarity such as cosine distance. This method is highly scalable but loses fine-grained query document interactions. BindEncoders are ideal for large-scale retrieval tasks where speed is essential, but may sacrifice some accuracy. CrossEncoder accepts the query and a document chunked together as a single input pair into the transformer, calculating a deep attention-based relevancy score. It is incredibly accurate but computationally heavy and slow, which is why it's often used as a second-stage reranker. CrossEncoders provide fine-grained query document interactions, improving retrieval quality. Encoders are fast and scalable, embedding queries and documents independently. CrossEncoders, by contrast, process query document pairs together, offering higher accuracy but at the cost of speed. In RAG systems, BindEncoders are used for initial retrieval, while CrossEncoders act as rerankers to refine results. Combining both methods balances performance and precision. Errant document retrieval, or small-to-large chunking, decouples the text used for embedding from the text passed to the LLM. Documents are split into very small chunks for embedding and retrieval, enabling precise semantic matching. Each small chunk maps back to a larger parent context window, which is delivered to the LLM for generation. This strategy improves retrieval precision and generation quality. Hierarchical node parser builds a structured relationship tree out of a document. It breaks text into parent nodes, large sections, and child nodes, subsections, or paragraphs. If a retrieval step pulls multiple child nodes belonging to the same parent, the system can automatically roll them up into the parent node, providing cleaner context for generation. This tool is essential for organizing complex documents in RAG. Metadata filters are structured attributes, such as date created, author, department, or document type, attached to individual chunks. Extracting metadata during chunking allows you to pre-filter or post-filter vector searches, drastically narrowing down the vector space before executing similarity calculations. Metadata filters make retrieval more efficient and targeted. During chunking, extracting metadata such as creation date, author, or department is crucial. This metadata can be used to filter searches, ensuring that only relevant chunks are retrieved. By narrowing down the vector space before similarity calculations, metadata extraction improves retrieval efficiency and accuracy in RAG systems. English text, a standard rule of thumb is that one token is roughly equivalent to 4 characters, or 100 tokens equal approximately 75 words. This approximation is crucial when calculating chunk constraints for embedding models that measure limitations strictly in tokens. Understanding token-to-character ratios helps optimize chunking strategies for RAG. Vanilla sentence-based chunking splits documents into individual sentences. However, this method often lacks sufficient isolated context. Pronouns and references can lose their meaning if related sentences are separated into different chunks. This limitation makes vanilla sentence chunking less effective for accurate retrieval and generation in RAG systems. Query rewriting is a concept in RAG fundamentals where user queries are expanded, rephrased, or broken down by a lightweight LLM step. This process optimizes the query for vector similarity matching, ensuring that ambiguous or poorly phrased queries are transformed into descriptive prompts. Query rewriting improves retrieval accuracy and user experience. Users often submit short or ambiguous queries. Query rewriting uses a lightweight LLM to expand and clarify these queries, making them more descriptive and optimized for vector similarity matching. This step ensures that the retrieval system can find the most relevant chunks, improving the quality of generated responses. RAG systems are particularly valuable for enterprises, allowing AI models to access private or dynamic data without costly retraining. By integrating retrieval and generation, businesses can leverage up-to-date information for smarter decision-making. RAG empowers organizations to build AI solutions that are both accurate and adaptable. One of the main advantages of RAG is its ability to mitigate hallucinations in AI responses. By grounding answers in retrieved, verified context, RAG ensures that the model's outputs are accurate and trustworthy. This is especially important for enterprise applications where reliability is critical. RAG enables AI models to access dynamic, changing data sources such as enterprise databases or real-time feeds. This flexibility allows organizations to keep their AI solutions current and responsive without the need for frequent retraining. Dynamic data access is a key benefit of RAG systems. By retrieving only relevant chunks and avoiding the need to process entire documents, RAG systems are cost-efficient. They reduce token consumption and API call costs, making AI solutions more affordable for enterprises. Cost efficiency is a major advantage of adopting RAG architectures. RAG systems optimize performance by balancing chunk size, retrieval accuracy, and generation quality. Experimentally tuning these parameters ensures that AI models deliver fast, accurate, and reliable responses. Performance optimization is essential for building scalable and effective RAG solutions. RAG systems can combine dense and sparse embeddings to maximize retrieval performance. Dense embeddings provide semantic search, while sparse embeddings ensure precise keyword matching. Using both types allows for flexible and powerful retrieval strategies, improving the quality of generated responses. Implementing RAG involves setting up ingestion, chunking, embedding, retrieval, and generation pipelines. Enterprises must choose chunking strategies, embedding models, and retrieval methods that fit their data and use cases. By following best practices, organizations can build robust RAG systems that deliver accurate, context-aware AI responses. To ensure optimal performance, RAG systems should be validated and tuned using grid search and metrics. Experimenting with chunk sizes, embedding models, and retrieval parameters helps find the best configuration for accuracy and efficiency. Continuous validation and tuning are key to maintaining high-quality AI solutions. While RAG offers many advantages, it also has limitations. The quality of generation depends on retrieval accuracy, and poorly chunked or embedded data can lead to incomplete answers. Understanding these limitations helps organizations design better RAG systems and avoid common pitfalls. The future of RAG is bright with ongoing advancements in embedding models, chunking strategies, and retrieval methods. As AI technology evolves, RAG systems will become even more powerful, enabling smarter, more reliable enterprise solutions. Staying updated with the latest developments ensures organizations can leverage RAG to its fullest potential. To build effective RAG systems, follow best practices, use structure-aware chunkers, extract metadata, combine embedding types, and validate performance. These steps ensure that your AI solutions are accurate, efficient, and adaptable. Best practices are the foundation for successful RAG implementation. RAG fundamentally changes how AI models access and generate information. By integrating retrieval and generation, chunking documents, and optimizing embeddings, RAG systems deliver accurate, context-aware responses. Understanding the fundamentals and best practices is key to building robust, enterprise-ready AI solutions. As you implement RAG, remember to validate, tune, and stay updated with the latest advancement. This video, we've covered the essentials of Retrieval-Augmented Generation, its purpose, pipeline chunking strategies, embedding types, and best practices. RAG empowers AI to access dynamic, enterprise data, mitigate hallucinations, and deliver reliable responses. By mastering these fundamentals, you can build powerful, adaptable AI solutions for your organization. Thank you for joining us on this journey through RAG fundamentals.